Hello, welcome to video 7 in the Advanced Mathematic Modeling. In the last video we have looked at discrete and continuous distributions of random numbers. We have seen that we can visualize the distribution either by the probability density function or by the cumulative density distribution, and in this video now I want to give some examples. And so, as you will see there, most probability distributions can be described with just a few number of characteristic types, and it's a good idea to know about them. And maybe the most fundamental or most simple distribution is the uniform distribution. And I now take first the example, a uniform continuous distribution. So we have a continuous random number and want to have the probability for this random number, and then we say it's either a constant or 0. Maybe first I show you the picture. We plot the distribution. So here we have the random number x. I want this to be symmetric around 0, and here we have p of x. And now I want a random number which is in a certain interval from -a to +a, and I want this to be uniformly distributed. So that means all probabilities are equal in this interval. Now, in order to normalize the whole thing, the height of this must be 1 over 2a, because then the probability to be between -a and +a is exactly 1. And so the probability is 1 over 2a if the absolute value of x is smaller than our constant a, and 0 if x is larger than a. And so that's the uniform distribution. Now that's the PDE. So how does the cumulative density function look like? So we put again here the axis. Now remember, we need the integral of this function until the value x. So it's the probability to have a number smaller than x. So this is a function. So first let's plot the characteristic values -a and a. And the function minus of x, we want to plot this, and the CDF is a quantity which goes from 0 to 1. So we know that's the range of values that we can have. And then for values smaller than a, this is 0. And then we know to integrate the constant, which gives us a linear function. So this increases linearly until at the value a we have probability to have a random number smaller than a. It's exactly 1, because that's the whole rectangle. And after this, it's again constant. So that would be the CDF. And this would be the PDF. Now you can see, maybe I write this here again. So that was the definition of the cumulative density function, and you can see, I mean, if you just integrate here this rectangle, then we come to this function. Now you could ask, why did we take here the smaller sign? Couldn't we have taken a larger sign? And of course, we could also have defined the CDF in the different way. We could have said p larger of x. That's the integral from x to infinity, p x prime dx prime. That would also be a valid definition. And you see that they just from one quantity here you can calculate the other one. So this means that here this p larger from x equals 1 minus p smaller from x. And so we it doesn't matter what we take this as the CDF, but one could also have taken the other one. And this would then be a function which is just decreasing here, decaying linearly. And there you also, so you see we have two different possibilities to visualize the distribution. And as I said here, with the uniform we see more the characteristic aspect. Also with the PDF we see more the characteristic aspect of this uniform distribution, namely that it's flat, so that all values or all random numbers in this interval are equally likely, which we don't see so easily here in the CDF. And the CDF is always a function which is monotonously increasing between 0 and 1, and they all will look like this. So I much prefer to work with these PDFs because it gets much better insight into what's going on. Now another question is, how can you generate such a number in the computer? It's a non-trivial fact that with the computer we can generate random numbers, even though the computer is a deterministic machine. But what the computer is doing with random numbers, it's calculating a sequence of deterministic numbers which mimic a lot of properties of real random numbers. And in the exercises, in order to do some modeling and so on, we need to be able to draw random numbers in the computer. And very often, to obtain a random number from a uniform distribution, we have the command rand. That's the command in most programming languages. And rand, maybe we need here parentheses depending on the language that you use. This gives us a uniform distributed number, uniformly distributed random number. In the interval 0 and 1. So this is what the computer gives us. And but now what do you do if you need a random number which is, for example, in a different interval, for example here from -a to a? Then either in your library you have some options to the function, when you call the function rand to give you the interval, or you make a simple variable transform. So for example, what I would do, I would just calculate 2 times rand -1. This now gives me a random number in the borders -1 and +1. And then I multiply this by the constant a. And this gives now a random number between -a and a. Yeah? And we will see this more systematically later. In order to generate random numbers from a desired probability distribution, we will typically use randomly distributed numbers at the interval between 0 and 1. and then make some variable transform to go to this distribution that we want. So that was the uniform distribution, one of the most basic distributions. And the second really fundamental distribution is the Gaussian. Or normal distribution. And the name normal distribution already implies that it's a distribution that's very often expected for things to happen. And so how does the Gaussian look like? Again, we have here x-axis, we have a distribution symmetric around 0. We have here a p of x. And now we have a more roundish distribution which has a maximum at 0, decays to the outside. I think you all have seen Gaussian distribution, and how we write this down mathematically. So we have here normalization factor 1 over 2 pi. And then we have a parameter sigma that gives us the width here. We will later see the sigma is the standard deviation, but this I don't have introduced this yet. But so it's just a parameter. And then we have here an exponential function minus x squared over 2 sigma squared. Gaussian function, and so this is a function, which has a tendency as a max at 0. So we have random numbers which with high likelihood are around 0, but then decay for deviations from 0. We will later in the course also see where this comes from and why this is so important. In the moment, this is just one important example. So that's again the PDF. So how does the cumulative distribution look like? So we have x, and plot here again p smaller of x. Again, this is bounded between 0 and 1, and it's now again a function which is increasing from 0 monotonically to 1. Here at 0 it's 1/2. Increasing and then goes to 1, and here it comes from 0. Maybe to see the difference, I also make this here colored. And so again, you can see the difference between the PDF and the CDF. You see the CDFs look rather similar, whereas in the PDF you directly see, here we have a tendency to have random numbers around 0, and here we have this flat plateau. So for the CDF cumulative distribution of the Gaussian, there is no analytic, expression. And so this function is so important, it gets a special name. It's the error function. So to write it down precisely, this is 1 over 2 times 1 plus the error function of x divided by sigma and square root of 2. But we just have to remember, okay, it looks like this, and basically this is the error function. So how do we get a Gaussian random number in the computer? in the computer. So this is the example where it's not so easy to generate this number from a uniform distribution by some variable transform. And also this Gaussian numbers are so important. So most computer languages have this also built in, and there you call just rand n be normal, and this gives you a Gaussian number with standard deviation sigma equals 1. But for example, if you multiply this by sigma, then you get a random number which has a width or standard deviation sigma. So with this, functions, you're able to generate uniformly Gaussian distributed functions in the computer. Let's have another example now, which we also need important. Let's take a discrete uniform distribution. This we have seen quite often. So now we have discrete random numbers pi, and so first maybe let's draw our distribution. Here we have pi, now it's discrete, and you just want to have from 1 to n numbers. So our distribution looks like this. All probabilities are equal, since this should be normalized. So the probability is 1 over n, so that the 1 over n, so that the sum over all of them equals 1. For e equals 1 to n. And we have seen this in fact already. For example, if we have a coin O, and we have n equal 2, and for a dice we have n equal 6. So we've seen the examples. We used a lot. Coin and dice throws are just discrete uniform distributions with a certain n. Now, how is this in the computer? Again, this depends also on your language and your libraries, or if you have MATLAB. If you started MATLAB like me 20, 30 years ago, then random libraries were not so nice. So at this time, you just generated a continuous random number, multiply this by the constant n, so to have a continuous random number between 0 and n, and then we take the function 0 to transform this real number into a natural number. So this is, for example, how I would have calculated discrete uniform distributions. But nowadays you have functions like rand int or something like this, which directly gives you discrete uniform random numbers in a certain interval. Yeah? And with all these functions, when you want to see really what your computer is doing in MATLAB, just use the help, built-in help, which gives you all the detail that MATLAB now, all the service that MATLAB provides to generate your random numbers in a certain interval. So the generation of random numbers in the computer is really an art to have a good library. In earlier times you had to be very careful that what you calculate in the computer is really a random number which makes sense and is, doesn't, how to say that it's not that it's random enough for simulations. Nowadays most languages come with built-in libraries which provide excellent random numbers. If you want, we can also look at this a little bit more in detail, how the computer is able to generate random numbers. If you would like to do this, just say this in the forum and then maybe I can cover this also. So this was a video about here 3 distributions, and I have chosen these 3 distributions not only because they're important, so here blue is always a distribution, but also because these are the 3 distributions which generate us the random numbers which we will use in the exercises, and basically all other distributions are the random numbers we generate based on these functions. So what's now in the next video? So now, I mean, so far now we have seen examples of distributions and we can plot them, visualize them, but now the next thing is we would like to characterize such distributions. What are the dominant properties of such a distribution and how can we measure them quantitatively? This we will do in the next video. Thank you.